Hello, I'm Ritchie. I'm going to talk about high entropy alloys and their damage tolerance. So let me try and share my screen so I can show the, okay. So this work was done with Mark Astor and Andrew Miner at Berkeley with several postdocs. This was funded by the Department of Energy, US Department of Energy. So I want to talk about these high entropy alloys, which are of course multi-component, multi-element, multi-principal element alloys. I want to talk about basically the cobalt, chrome, nickel-based systems, which are FCC systems. And most of the ones I want to talk about are going to be single phase. Talk initially about the counter alloy, then about the three component, the so-called medium entropy alloy. Mention a little bit about dual phase or trip alloys, and then talk about what we think is a kind of important topic, which is this question of the local order. Okay, so just to recap on some old stuff, this was the original counter alloy. This is the chrome, manganese, iron, cobalt, nickel system. We got interested from listening to Iso George, who'd shown this beautiful work that as you decrease the temperature down to liquid nitrogen temperatures, not only did this alloy get harder, but it also got much more ductile, got increased ductility. We did the fracture toughness tests and got remarkable numbers around 200 megapascal root meters for the toughness. These are JR curves. And for the crack growth toughness, these initiation toughness, crack growth toughnesses, we got numbers around over 300 megapascal root meters. These numbers stayed about the same at liquid nitrogen temperatures, which is unusual because you expect things to drop at lower temperatures, of course. Classic ductile fracture, you can see this here. So why do these materials have such amazing damage tolerance? Working with Yu Chien in Zhejiang University, we looked at some in situ TEM, and there are mechanisms here that promote both strength and ductility. What I call a duality of mechanisms. If you look, you see planar slip with undissociated dislocations, which would, and it's very ponderous. It's high lattice friction in these materials, which gives rise to, we think, strength, yet the partial dislocations, and if you look at this one going to come in here, move extremely fast, and they're blocked, of course, by the slip band. So these are mechanisms where you get ductility, and we actually see bridging across the crack tip here. I think this is possibly an artifact of the thin film, because these were done, of course, in the transmission electron microscope. But if you look carefully, you can actually see twinning in these little bridges. So this material doesn't twin at room temperature, but it twins at low temperature. The twinning and these duality of deformation mechanisms give rise to steady strain hardening. This is the classic recipe for intrinsic toughening in metallic structures. The strain hardening, of course, increases the strength, but it also delays the necking, the instability, and we get remarkably high toughness. You can see that the massive twinning that forms when you go to lower temperatures. You can see here the thin deformation twins that form readily at liquid nitrogen temperature. You don't see them at room temperature in this alloy, except in these very high strain situations, as I showed you here. We also looked at a three component where we took the manganese and the iron out, and this was even better. We got numbers of where strengths at liquid nitrogen temperatures, again, room, dry ice, liquid nitrogen, strength above about 1.2, 1.3 gigapascals, but with 90% tensile ductility at liquid nitrogen temperatures, which is pretty remarkable for a material, any material. We did the JR curves again, and the toughnesses are remarkable. They're 200 megapascal root meters at room temperature. When we go to liquid nitrogen temperatures, we're up to 270 megapascal root meters. This is an initiation toughness. If we look at the crack growth toughnesses out here at delta A max, we're getting numbers like 450 megapascal root meters. These are mind-boggling numbers. They're just remarkable. Of course, this material twins even at room temperature. It's a stronger material, which means twinning is stress-induced. And so we get a hierarchical network of twins, but you get the same duality of mechanisms. Now, in the counter alloy, you had this lattice friction because of the multiple elements, but you had the low stackable energy. Now it's even lower stackable energy. And in fact, we see, as I said, a hierarchical twin network. The twin boundaries act to arrest dislocations. which is the strengthening mechanism, of course. Yet by the same token, if you look at them, the partial dislocations will move along the twin boundary. So they're highways for deformation as well. So you have, of course, the strengthening mechanisms and you have ductility mechanisms. And if you go to lower temperatures, I'll add in a minute, you get motion on these slip bands again, but you'll see you get massive cross slip off the slip band. So a lot of mechanisms that promote ductility and also promote strength, which occur in parallel. And of course, these materials do have really remarkably high toughness. I mean, this is an Ashby plot here, not quite as strong as metallic glasses, but extremely high toughnesses. And these numbers are absolutely off the scale. We've looked also at lower temperatures where the maximum properties are. We've done TEM at 93 degrees Kelvin. This was a paper in Materials Today last year. And you see these mechanisms that operate similar sets of mechanisms. This is, of course, the twinning mechanisms. You can see them operated, primary twins coming down here, secondary twins shooting off in the other direction. We see plenty of ductility. We see motion on the slip bands, and then this massive cross slip, which comes off the twin bands. This is predominantly a low temperature mechanism. And we see, of course, as before, the boundaries blocking slip as both the twin boundaries and so forth. But you can see at the intersection here, you're generating more dislocations, you're generating slip and twinning. So there's a lot of mechanisms that can generate both the strength and ductility. Remarkable materials, there's no question about this, that there's a synergy of mechanisms. Just one other picture here. I talked about the motion of partials along the twin boundaries. This is, you see this at low temperatures as well. In fact, it's even more prominent. We've also looked at fatigue. I'm not going to say too much about this because there's a lot of story here, but in fact, the fatigue properties, these are crack growth properties, actually increase at lower temperatures too. There's an elevation in the threshold at low temperatures, not necessarily due to the same mechanisms, they're due to crack closure. You see a faceted mechanism at lower temperatures, but you also tend to see twinning at the lower temperatures, which you don't see at room temperature because fatigue is at lower stresses, of course, so you don't necessarily activate twinning. And the twinning gives you again, a rough surface, and you tend to promote more crack closure, which puts the threshold up. We've looked at the 3-component system as well. Again, we've looked at coarse and fine grain, and the coarse grain, as you might have expected, tends to generate much more crack closure because of the fact that it's a higher strength material, the crack open displacements are smaller, and you get more contact in the surfaces. And in fact, if you compare the 3-component, 4-component, the 3-component is the better material. I think because there's a greater influence of crack closure. What about some of the other systems? Ravi did some nice work. We looked at a whole range of trip, canter, and a dual phase. We looked at a dual phase system. This came via Ensu Park. A lot of this work was done by Bernd Glodowitz, of course, who worked with me a few years ago. Here is the dual phase system. It's a nominal canter type alloy, not quite equiatomic, of course. And the dual phase system has a epsilon martensite as well as the FCC austenite, and you can see this, the martensite's harder, it elevates the strength, it elevates the strain hardening, so this should be a tougher material. How does this work? Well, when this system when you look at it in situ deformation, you see a lot of lomocotral locks form. These are when you get two Schauffele partials form on intersecting 111 planes, and they form this A/6 dislocation, which is basically sessile. So it locks, it's a sessile dislocation. And if you look at how the deformation takes place, we see a lot of these stacking fault networks. These lomocotral locks, we think of the key that anchors this network. And at the base of these things, you start to see where the hexagonal phase forms. There's a lot of, the stacking fault there as well, but this is the base of where these hexagonal form. And this is a pretty intense network to block dislocation. So we get a lot of particularly high strain hardening. You can see this in some of these mobile stacking faults will basically cause slip bands to completely cease. You want the slip band hitting here, that's the immobile stacking fault. and it just totally blocks dislocation motion. So this should be good material. If we look at the toughness of these materials, and this is comparing with the counteralloy, the trip material, I haven't looked at that in detail here, the TWIP material, and the dual phase, what I'm looking at, you can see the dual phase is good toughness, but it's not as good. These are R curves, again, JR curves, not as good as the counteralloy. But the really telling thing is when you look at this from the perspective of lower temperatures, these are again JR curves, red is room temperature, and blue is liquid nitrogen, dry ice is in between. And the counteralloy, of course, gets much, much tougher at lower temperatures. But if we look at the dual phase and the trip system for that system, of course, you're getting good, better strain hardening, you're getting higher strength because of the martensitic phase, it should be good, but you don't see the higher toughnesses, and they certainly don't get tougher at lower temperatures. And we think the simple reason for this is that the transformation is good, it absorbs energy, it causes strain hardening, but the resulting phase is not very good. This epsilon martensite HCP, not a particularly tough phase, certainly not at room temperatures. And so it isn't a particularly desirable thing from the point of view of toughness at lower temperatures. Even at room temperatures, the counteralloy does much better. So we've got these elements, we've got these multi-element alloys that they have exceptional mechanical properties, toughness, strength, ductility. This is basically the cobalt nickel. Chrome materials are really the best for that. We talk about the special properties, you know, they have their high entropy, sluggish diffusion, lattice distortion from the multiple elements. But we're really talking mostly about random solid solutions, but are they random? The question that we've been asking ourselves, with all these multiple principal elements, is there possibility of unconventional atomic structures? Is there possibility of elemental distributions, clustering, even short-range order? So this is what we've looked at. And is it there? One, you might expect it to be there. And secondly, does it have any effect? So we first of all looked at this a few years ago, looking at DFT. This was John Ding's work, doing basically DFT Monte Carlo simulations on, we looked at the equimolecular three-component, because it's easier to deal with, and looked at basically what we'd expect in terms of local ordering. We found certain pairing of atoms was preferred. This is the so-called Warren-Cowley parameter. And we found, for example, that chromium-chromium bonding was not favored, but chromium-nickel and chromium-cobalt bonding was favored. And there's only one study at this point that had been done with X-rays, an indirect study, which had suggested that, in fact, chromium preferred to be nearest neighbors with nickel and cobalt. So we looked in more detail with this model, and we first of all tried to calculate what the stagnant energy is. What's interesting about this is the stagnant energy for the three-component, when you do DFT calculations, always comes out negative, which means the whole structure is hexagonal. But if you measure it by conventional means in any experimental experiment, you're going to get a positive number. Why? Well, we computed the stagnant energy for a purely random solid solution, and then put increasing degrees of local chemical ordering, short-range ordering, and we got a dramatic change in the stagnant energy. Numbers that varied from about 70 millijoules per meter squared. Now, these are only a small number of atoms, right? A couple hundred atoms, so you have to question all these things, but that was what it was showing. It was showing that short-range order had a dramatic effect on the stagnant energy, consistent with what people see, and the fact that you know that stagnant energy has a marked effect on deformation and dislocation activity. If you look, we also looked at this, the energies of the hexagonal and the cubic phase, the phase and cubic phase, and you can see it when you're in a random solid solution, hexagonal has the lowest energy, and that's what the negative stagnant energies come out to be. But as you go into increasing degrees of order, that changes, and then with enough order, you will get basically the FCC being the stable phase. You can see a bit of hexagonal in these materials. Actually, Mike Mills has seen little bits of hexagonal that's forming, but it looks like that we think that most commercial alloys then have short-range ordering because of the fact that they're FCC. We also found that it affects the twin boundary energy. I don't have to talk about this. We also find it affects the formation of interstitial energy, formation energies for interstitials and vacancies, which does have a bearing perhaps on why these materials are good for radiation damage, as has been pointed out, because you tend to delocalize the interstitials maybe. It affects dislocation mobility, it affects slip mode. This is all came out of the for the DFT calculations. Now, you could question these, of course, because some of the atomic volumes don't quite fit. It's DFT. There is a magnetic component in this particular alloy, which we think is, we're just working on that now, which we think is very important and may be one of the primary sources for short-range order, but that's another story. But our quest now is, can we actually see it? Can we see short-range order? And this is a very difficult thing, of course, because the contrasts from the atoms are very, very, not very different in these systems. They're all the nearest neighbors on the periodic table. So the first thing we worked on was, this was with Yu Qian in Zhejiang University in China, was to look at two radically different systems. Look at the counter system. These are all elements that are neighbors of the periodic tables. They're all sort of similar elements. But we looked at also an alloy where we replaced manganese with palladium. Now, palladium has a big difference in electronegativity and a big difference in size. So we might expect some degree of ordering, perhaps a local ordering. The counteralloy seems relatively random and homogeneous. We don't see much. We're looking here. This is basically atomic resolution EDF, and you're looking at the composition of columns of atoms. We don't know the order in those columns, but we can get the composition. We're looking at atomic mapping of composition, and it's pretty homogeneous in the counteralloy. But in the alloy which contains palladium, we see a lot of aggregation of certain elements. It's not just the palladium elements. All the elements tend to aggregate over certain variations. Instead of being all at roughly 20%, you see variations of the composition varying from, in the case of palladium, from a few percent up to maybe 40%. And so we map these out. It's difficult to say it's clustering, but we use the term that Khachaturian came up with of concentration waves. There are sort of repeatable waves of concentration you can see in these systems. It's much larger scale than you'd think with atomic local short-range order, where you're, that's the interaction of atomic first or second atomic shells. Here, that's about 0.5 nanometer. Here, we're talking somewhat larger, about 3 nanometers. But this would act or serve to roughen the lattice. And so we'd expect this to give us different dislocation motion. And in fact, you see this. I showed you earlier that if you look at dislocation motion, you see these planar slip bands, but then for some reason, the dislocations will stop, and then you get this massive cross slip that comes out. So we can't quantify it here, but this is consistent with the notion that this local order may exist. The other thing that's interesting here is these local variations in composition give rise to differences in atomic strains, of course, and we can measure those. This is a technique called geometric phase analysis methods. And you can, if we look at the counteralloy versus the one with the palladium, and you can see this is varying. Blue is compression, red is, so yellow is tension. There are much higher local atomic strains in the lattice in that element, which has the higher short-range order. So we think this is, there is an ordering that's seen in the scale of 1 to 3 nanometers. But what about what people really understand by short-range order? We've looked at this with, this is Andy Miner's group working with us on the NSEM, looking at using an energy filtered TEM. Difficult to see short-range order. The contrast from these elements is pretty similar. We use an in-column energy filter, which filters out the inelastic scattered elements. This came out in Nature a couple of weeks ago. And we looked at two structures of the 3-component system again, one which was water quench, which we just assumed was random, and one which we'd aged it at 1,000 degrees C and slow cooled it, but we expect to see short-range order. We see streaking on the diffraction spots. You can see the streaking here, which you don't see in what we assume to be random structure. You put the aperture on this, and you can start, and you take a dark field, and you can start to see these sort of white spots, which are indicative of local order. You don't see it in the one that's basically as quenched. We can deconvolute that and get some notion of local domains of ordering. This is a histogram of that, and they sort of maximize or just under 1 nanometer. There's a lot that goes with this. There's a lot of things that could also be due to. We've done exhaustive studies, we think, to prove that it is local order. I won't go into details, but we think this is the first direct evidence of local ordering, and now we're assuming we're on the half nanometer type scale. So if order's there, what effect does it have? Well, we do see differences. We do see a change in slip mode. The random structure seems to be wavy slip. It turns to planar slip in the case where we have short range order. We see a big difference in the spacing of the partial dislocations, which is indicative of stackable energy. This one is the one which basically is, we assume to have, where we see local chemical ordering has a smaller separation, has a higher stackable energy than the one which is where it's as quenched. We also see changes in the mechanical properties. These are doing small, these are nano indentation tests, and these are tiny stress strain curves on little tiny tensile samples. This, the red again, of course, is the one that's random, and this is the one that has, we think, local order. And we see changes in strengths, but particularly changes in strain hardening and so forth. We even see small changes in modulus, which is not unusual for short range order. Now, we don't know exactly where this order forms. It's somewhere between 1,000 and low temperatures. We're trying to map a TTT curve out because there's obviously a thermodynamic cutoff above which it wouldn't form. It's limited by diffusion as you go down in temperature, even though the driving force is greater. We think, by the way, that we can see this distinction because we're looking at very thin structures that we're quenching, but it may be very difficult to suppress short range order in this thing, that most structures will have this in. And the big question is, do you do thicker sections now? Is there something which you might be used for the properties of the material used in real life applications? Can you actually change the short range order? That's a good question. So let me finish by saying that we've looked at these multiple principal alloys, particularly the FCC, cobalt, nickel, chrome, nickel system of high entropy alloys. These have truly exceptional mechanical properties in terms of strength, ductility, and toughness. It's motivated, particularly at cryogenic temperatures, it's motivated by a synergy of deformation mechanisms, ultimately ending in extensive nano twinning, which gives us steady strain hardening, hardens the material, delays necking, and gives rise to what we think is the highest toughness of any material to date. It's certainly on this Ashby plot looks like that. And it does this, it retains strength, so it has really good damage tolerance. There are mechanisms for this. I said this sequence of deformation mechanisms. The question that we think is very important, though, is this may be associated, may be motivated, may be promoted by the presence of local ordering. The DFT and MD calculations certainly show that to be the case. We believe now we've seen it at several size scales. The work that Yuqian did in China and the work that we've done here in Berkeley. We think we have definitive proof for the fact that it exists. The question is it important? This is a controversial topic, by the way. I mean, people like Bill Curtin think that it may or may not exist, but certainly it's not that relevant. Well, it may be. And in fact, we think it really is, in terms of, when you've got an ordered structure and dislocation start to move the orders to, lost, it's removed, and that has effects, things like strain hardening and the like. And the sort of the salivating thought in the future is that you've got these alloys which are topologically ordered yet chemically disordered. There may be a way of using chemical ordering to locally tune the properties, and that is a nice, interesting thought. Whether it's a reality, we'll have to see. Thank you very much.